all of you. Today, Dr. Vijay Raj Singh, as a coordinator of Science Lecture Series Season 2, takes this opportunity to welcome you all to the webinar by the Physics Department at Central University of South Bihar, Gaya. Honorable Speaker Professor Henry Wong, respected head of the department, and my dear friends, I extend a warm welcome to all of you and participants to this webinar today. We all have gathered here for a webinar on a very interesting topic, neutrino physics overview. I ensure you all that you will truly enjoy this session and will definitely take some learnings home today. Now I request Head of Department, Professor Venkatesh Singh, who is the chairman of this session, to introduce our esteemed guest of today's webinar and request him to present his talk. Professor Venkatesh Singh.
Okay, thank you, Vijay Rajji. Hello, everyone. Namaste and very good morning. This is Venkatesh of Central University of South Bihar, Gaya. Today, I welcome all of you on behalf of the organizing team of this virtual science lecture series, which is organized by the Department of Physics, School of Physical and Chemical Sciences, Central University of South Bihar, Gaya. I would like to thank all the online participants for showing their interest and taking part in the season 2, 6th lecture of this science lecture series 2020. Today, we have the pleasure of having one of the world-renowned scientists, a legendary astroparticle physicist, a very dynamic researcher, very popular and humble person, my teacher, Dr. Henry T.S. King Wong from Institute of Physics, Academia Sinica, Taipei, Taiwan, with us. I welcome you, sir, from the bottom of my heart. Dr. Henry Wong, sir, will speak on neutrino physics overview. Dr. Henry Wong did his BA first honors in physics from University of Oxford, England, and earned doctorate in physics from the California Institute of Technology, Caltech, USA. Presently, he is professor and serving Institute of Physics as Deputy Director since 2013. Dr. Wong was a staff member of CERN, Geneva, Switzerland before joining Academia Sinica, Taiwan. Dr. Henry is a member of various international advisory committee and honored with various national and international scientific awards. He is a founder, spokesperson, and lead principal investigator of Texono collaboration. Texono stands for the Taiwan Experiment on Neutrinos. Dr. Wong is well-traveled and nationally and internationally very well-known figure in his area of research. I hope his today's lecture will show seeds of knowledge and will motivate master's students towards astroparticle physics. I believe this lecture will be a beautiful blend of theory and experiment, basic and advanced knowledge of physics, and would equally draw huge attention of the knowledge-loving undergraduate and postgraduate physics students, as well as young and dynamic faculties. As I have always mentioned before each lecture, that our speakers are internationally renowned in terms of their area. Therefore, they do not need detailed introduction. However, for curious, young and motivated participants, we have already uploaded his very short CV on the Science Lecture Series website and Facebook. Dear participants, colleagues, and friends, if you have any questions and queries related to this lecture, please write them down in the chat box. At the end of this lecture, Secretary of the Science Lecture Series, Dr. Puneet Misraji, will ask your question on your behalf. Once again, I welcome you, sir, and we are really grateful to you for accepting our request of delivering today's lecture, sharing knowledge and time with us for your very busy schedule. With these few words, I would like to request Dr. Henry Wong to please deliver his talk on neutrino physics overview. Dr. Wang, sir, please deliver your lecture.
Yes. Okay. So first of all, hello everyone.
Sir.
Thanks from my heart, and also thank you for Professor Singh for a nice introduction, as well as organizing the event. To you, learning physics from an internet talk we do, but also to me, giving a talk through the internet is also, this may be my 4th or 5th times doing it. So I'm also learning how to do it as we get along. So we are learning this new format of teaching and learning together. So first of all, so I am heard. You see my video, my face, as well as you see my screen, right? If none of this if none of this has problems, you should shout, because I have no feedback from my end, except that I'm watching my screen. Okay, so if there's some technical problems, shout
Sure,
anytime. So for today,
Sure,
so we start. We'll have a survey, to show you the broad landscape, just like a very panoramic view of the subject of neutrino physics. A neutrino is an elementary particle, so we have to touch point.
Sir, just share your slides, sir. We are not able to see your slide.
You're not seeing my slides? You're not seeing my slides?
So there is, sir, there is. Venktesh sir, slide show ho raha hai. We are able to see.
But I can't see. Where.
Touch your screen again. Sir, touch your screen
Yeah,
again.
several times I'm touching, but I can't see.
Okay, so everyone. So you should
But we are able.
Okay, sir, please go ahead.
We can see the slides. We can see the slides.
Okay, that's great.
Right, and now I'm jumping to page 2, page 3, and so on. Okay, and also you are seeing my cursor.
Yes.
Okay. Now, so this bound to happen.
Yes, I can see.
Yeah, especially when all of us are new. So this is one of the things that we have to learn as we get along. So, but also we better get used to it now and more often, because this will be the new way of learning things for teachers to give classes in the future. It seems inevitable. So we better learn all the techniques and then I know all the problems now. Okay, so I understand that. So this is an audience of mostly fresh students in physics. We are not experts in particle physics, but there's no problem. We can still enjoy physics at whatever level. But I would get to a language that you should that everyone would appreciate, so we wouldn't get into much technical details, which is not important for today. And we would look at the broad landscape, just like sitting on a high plateau, surveying the whole broad area, enjoying the view, without getting into the details of every tree and every rock. So we would discuss neutrinos, as well as how it stands in the standard model, as well as astrophysics. And in particular, I would like to share the stories of neutrino oscillations, which is an advance in science, not just particle physics, but in science in the last 30 years, and something which started off when I'm at your age as a problem, but now it is textbook information. So this is I have the good fortune of seeing how a sentence, a paragraph in textbook would evolve from some speculative, everybody is not sure ideas to a real piece of knowledge that would last. And then where we stand and what we would be doing, and what the field is getting on, and then some outlook. Okay, so standard model is a particle physics. It's an understanding of the alphabet of the universe. So at this point, we have a good understanding, in fact, complete understanding of the so-called standard matters, including and then the alphabet in the universe, including of 6 quarks, 6 leptons, and they are mediated by forces which which can be interpreted as elementary particles, and they have their own antimatters. And all this would, from a quark would turn it into proton and neutron, and then proton neutron would turn it into the nucleus. The nucleus plus an electron will become atoms, and many atoms will become matter, and then becomes everything that we are familiar with. So this is in one sentence, this is how we understand the universe, and it is correct, with a compelling evidence that the universe really works like this. Yeah, and we talk about the alphabet, but also the grammar. The grammar is how these elementary particles interact, and there are 4 different ways to interact. They can interact by gravity, via weak or electromagnetic interactions, which is now unifying the framework of electroweak interactions and the strong interactions. And one can visualize. One can visualize what happens. It's like a cartoon like this when there are 2 persons throwing a ball on a ship, or 2 cannons, or 2 tennis players playing tennis ball on a skater. From far away, if the ball is commuting, transversing very fast, we don't see the ball, but we see them as if they are interacting. So this is our understanding on how elementary particles would interact. They exchange so-called just gravitons, photons, gluons, and doublons, and so on, which we cannot see because they are either they are very short range, not for our eyes. But then this exists, and with this way of understanding, we have very good confirmation on how the universe, how elementary particles behave, both the alphabet and the grammar of this language. And this language explains how matters behave. Okay, and then to a more technical audience, the cartoon of exchanging balls would becomes a page of formulas like this, which we will not get, we will not get into that. That is formula. But just to impress you, that for the students, that in physics, the ultimate language is mathematics. You have to turn it into formula, into numbers, to get ourselves convinced that we really understand what is happening. And through these notations, and through numbers, then we can make predictions. We cannot just say that the apple drops from top to bottom. This is correct, but this is not complete. We have to write down a formula that I can predict numbers, and then change, and then predict situations in order to show our complete understanding. But for today, we take it at a qualitative level, storytelling level. We didn't go to the maths. But if you would be turned into a professional, you need to learn about this language, just like a musician has to learn about the musical notations and so on. Yeah. Okay. So now, but I have also been not totally complete, and maybe even misleading. Just now in the first few pages, I declared that science is very great. We understand the universe. Full stop. But again, numbers comes in. Only with numbers, then we know where we stand. I didn't mention how much of the universe we understood. In fact, it is rather shamefully and rather embarrassingly, we only understand about 4% of the universe. So those 4% are the atoms, are the things that make us up. The hand is what you're seeing now is at the end, protons and neutrons and electrons. This we understand. But beyond that, it turns out that we have compelling evidence, experimental evidence, that the universe is much more complex, much more complicated than the stuff that make us up. On top of the protons and neutrons and hydrogen and carbon that give us life, this only makes up the periodic table. Materials in the periodic tables only make up about 4-5% of the universe, and the extra 90% is we have evidence that they exist, but we don't fully understand them, except that we managed to give them some names. 25% or 30% is around, it's called dark matter, and then around 70% is, we call it dark energy. Having a name doesn't mean that we understand them, but they are different, and this dark matter still at least obey the laws of gravitation, whereas dark energy do not. We only understand about 4% of the universe. So that means that now if you open up your eyes and look around you, we don't fully understand the room that we are in the minute level. In this room, there's not 90% of this 4% is averaging over universe. But of course, in our room, most of the materials are the standard model materials which we understood. But nevertheless, they are still dark energy and dark matter in the very room that we are sitting in. And so this poses a big problem as well as big opportunities for fundamental research for physics. We would like to understand what they are. So this is where we stand. And also in a one-page storytelling way, how the universe evolved from 10 to the 10 years ago. Now we have also very compelling evidence that 10 to 10 years ago, all the energy density of the universe is confined in the very small space, and then it started out with a big bang and a big explosion of this huge amount of matter density. It's not just energy, but energy density, which means that it's in a very, very small volume, and then slowly it expands, and then so while it expands, what happens is now this we can easily understand with our experience. As time goes on, the temperature drops, energy drops, temperature drops, and then what happens? Structures forms. So when structures forms, the quarks would combine to form nucleons, nucleons combine to form nucleus, nucleus get an electrons to get atoms, atoms becomes complex atoms, it becomes molecules, and becomes a material, become human beings, becomes all the beauty of the world. So this is a one sentence statement of how the universe, how the universe is all the complexity exists because time flows by, temperature drops, energy drops, structures forms. So now this is something that although we can be turned into very technical, very quantitative, but in a nutshell, this is what we have gone through. And all along, the only coherent, consistently correct language is physics. The physics combining the first 10 to the minus 42nd to the physics now is the same. So the science is based on that. The alphabet and the grammar have been the same all along. Only that at different epoch, because of different temperature, because of different energy, the manifestations would become different. The grammar is the same, but you can use a grammar to write poetry. You can also use the same grammar to write a novels of 10,000 pages. But the fundamental alphabet and grammar would be the same. So that creates the beauty of life. And it has been, and this story has been getting on for 10 to the 10 years, from a very small explosion to present days. Also, all the complexities of stars and galaxies and biology and human beings and so on. Okay, now we also have a good understanding since the last centuries where the nucleus has come, where our standard model matter has come from. Helium and hydrogen are the remnant of the first Big Bang nucleosynthesis. So the hydrogen around us, which indeed in our body is an organic substance. There's a lot of hydrogen. They are the remnant of big explosions 10 to 10 years ago in the Big Bang. Whereas slightly heavy atoms, the boron and lithium, they are produced by cosmic ray, and then an intermediate atoms like iron, like the silicon, which runs our computers, are in fact produced by hot stars. And the heavier one, copper, lead, uranium, and so on, are from supernovas. So we also have a good understanding on where everything around us comes from. Yeah, and they are different. So you can think about, you can appreciate that the silicon that runs our computer is not produced by us. It is produced by some stars light years from us, and they explode, sending the remnants over the universe, and some of them happens to arrive on the cube that clumps together to form what we call the planet Earth. And then human beings evolve, and then dig out some of and then do some mining out of some of the rocks and turn it into silicon and turn it into computers. So this is how the stories evolve. Okay, now so I give a well, now just now I use just 5 transparencies to, in fact, I can say that it can summarizing 2,000 years of human pursuit, starting from the ancient Greeks. They have been trying to understand the universe, the alphabet, and the grammar. Their answers over 2,000 years ago were wrong, of course. Were incomplete, of course. But the idea, the pursuit, the questions is right, and this is the most important. Asking the right questions is probably having the correct answers, because there are no completely correct answers. And now we focus now. So now after this very broad survey, now we focus on one particular alphabet and how it behaves. And this alphabet, this letter is the neutrino. It's one of the leptons in elementary leptons in nature. And so now we try to see what is the story behind the neutrino history. Now it's not only about now it's 2020, so it's a history of the human interactions. Although neutrino, of course, exists since the Big Bang, but human beings knows about this, is related to it only 100 years ago, starting from a continuous beta spectrum, and then we learn about various people postulate, hypothesize existence of neutrinos, really see it, measures properties, and then see it in an accelerator in the sun and have learned about more of the properties. And also we see neutrinos from the supernova, and we learn about that there are 3 neutrinos, and we learn about the neutrinos of particular properties called neutrino oscillations, and oxygen exists for the sun, for the reactor, for the accelerators, and everywhere. And we also observe neutrinos from the Earth. So a very brief history of the last 100 years. And indeed, it is one of the favorite subjects for Nobel Prizes, starting from Pauli, who postulated the neutrinos till 5 years ago with Kajita and Madonna. Now we don't. All these gentlemen are grandmasters in their field, and then we don't have to go into details of every one of them. But just to at least we should have an impression that this has been one of the frontier endeavors pursued in science since its birth for this 100 years, and then one of the favorite Nobel Prizes. Okay, now, so why do we know how it was born? Why do we know about, and how do we know our neutrinos? A little more than at the end of the 19th century, European scientists, learns about that things are more complex than classical physics. They find out that matters are not stable. Some matters are not stable. They can disintegrate. They can disintegrate. They can decay. And there are different kinds of decay. One is the decay is some materials can emits a beta particle. They call it beta at that time because they're running out of words. There's an alpha, beta, gamma. But now we call it beta particle as electrons. So some matters they learn that would emit electrons. This is a totally not described in classical physics. Now, okay, so this is a big discovery. Matters are unstable, but now scientists can ask finer and finer questions. So we ask not only electrons, what are they emit, but also the energy of the electrons. And if it is a two-body decay, so-called an A decaying to B plus electrons, we would expect that the electron is monoenergetic. The energy being half between the sharing of between A and B. A is heavier than B, so when A decays, it emits electrons and B, and then the electron energy will be the difference between mass of A and B. But experimentally, what is observed is a continuous spectrum. So this puzzles scientists 100 years ago. It puzzles because, and then there are, of course, at that time, when we do not know the answer there, and when we do not know the answers, we have many answers. One of them is, why do we have to say that somebody would challenge that the energy momentum is not conserved and other things? But now, by now, we know that a more dramatic hypothesis is the correct answers, and this is done by Pauli. So this three-body decay is 1915, and after 10 years, this Mr. Pauli would theorize that if it is a three-body decay, the first part, the parent nucleus, disintegrate into an electron plus a daughter nuclei plus something else, and that something else is not seen. So that something else should be light and should not intact too well. It didn't call it neutrinos, but then the idea would be postulated in 1930s, almost 100 years ago. And now, so fast forward, it takes 26 years before science would finally catch up and really see that for real. Now, Pauli is a Pauli of Pauli exclusion principle, already a very famous physicist. But then, of course, famous physicists need not always say the right things. So never trust them unless, again, back up by data. And Ryans and Cohen spent for 20 years from that point would have observed neutrinos. These particles, given the name is given by another famous physicist, Fermi, in a power reactor. So how it works is that neutrino, by now we call it anti-neutrino of electron type, would interact with proton, giving a neutron, and then also a positron. A positron would annihilate with electron, giving 2 gamma ray. So a positron giving 2 gamma ray, detected, and the neutrons would swim around for some finite but short period of time, say 100 microseconds. And after 100 microseconds, that neutron will be captured by, in this case, by cadmium, giving another bunch of gammas. So they put that detector, we don't have to worry about what the detector is, near a power reactor. Because there's there. Why do they put it in a power reactor? Because power reactor is fueled at the end by a lot of beta decay. And we know that beta, and Pauli tells us that beta decays emit neutrinos. So they look at things that have a burst of light, bing, and then after 100 microseconds, another bing, bing, we look for bing. It's easier to look for bing because bing has a lot of background. And by doing and comparing the bing be with reactor on and reactor off, there are more bing during reactor off, and so during reactor on, then they concluded that they have seen the particle neutrinos. So this is how neutrinos was discovered in 1950s. So by now, we use neutrinos. We have the complete. At that time, this is discovered a new standard model, new elementary particles. So this is a new alphabet. But then now the whole grammar and the whole scientific program is like this. So in the standard model, we want to remember that page of a lot of formulas. In that formulas, a couple of terms is reserved for neutrinos. We want to know how the terms looks like. So-called the Lagrangian of the neutrino mass. We don't have to worry about how the terms is written for today, but there's such a term exists. And now we know that the terms is non-zero because the neutrino mass is finite. And that terms depends on some parameters, measurable parameters like neutrino mass and neutrino mixing. But we don't measure neutrino mass in neutrino mixings. We measure their consequence: neutrino oscillations, neutrino magnetic moments, decay, neutrino decay, neutrino subbeta decay, beta decay spectrum, neutrino interactions. So we measure those, trying to learn about this mu and then uij parameters in L. So this is the sequence of events. And indeed, but in order to do this, this experiment measurable is related to particle physics, nuclear physics, astrophysics, as well as cosmology. Okay, so therefore, to study this, we need to learn. Different people have to learn about different things. And if we know this, we would learn about the structure and the composition of the universe, as well as the grand unified theories, the structures of the Lagrangian of that formula, which is one of the holy grail of physics. Yes, okay. So now, in order to study neutrinos, so that was the roadmap. This is what we want to do. But how exactly that we are doing those? In order to study something, we want to have this. We want to know where. We want to find out locate where those something comes from. What objects in the universe produces them? Just like we want to study the sun, we have to find something that can look at the sun before we can understand the sun. And so neutrinos, we want to study neutrinos by locating what are the neutrino sources. And by now we learned that neutrinos is everywhere. There's around several hundreds per cc. So in the room that we are sitting, every centimeter square cube, every cc, there are hundreds of neutrinos. So certainly there are more neutrinos in the room than human beings. And the neutrinos are produced from the sun, from the supernova, cosmic ray, reactors, accelerator, astrophysical sources, and also from the Big Bang. They are produced in many different things, and they have different energy. So this is the energy spectrum. From very low energy, micro electron volt, to 10 to the 18 electron volt, very high energy. So they are neutrinos from the sun, from the earth, from the reactor, from supernova, from the atmosphere, from cosmic ray, and from astrophysical sources. Out of this range, the range between sort of sub keV, several keV to 10 to 15 eV have observations. Very low energy and very high energy still remains to be observed. And so we have techniques to measure those neutrinos, to study them, and to find out what it is, how it behaves. So this is the progress of science. We have to learn how to measure it, see it first, and once we see it, then we try to understand it. So this has been what we have been doing in the last 100 years. Okay, so now, neutrino sources from anything from keV to TeV. TeV is 10 to the 12 electron volt. And there are sources from here, we call it wild, which is from natural, from the earth, from the sun, from the supernova, and from the cosmic ray. And but we can also produce it from radiative source, from the reactor, from the accelerator. Yeah. And the numbers to remember is that how much neutrinos? So we mentioned about hundreds of neutrinos per cc. Turn it into mass. How much mass are then of neutrinos? It is around 0.5%, 0.005 of the energy of the universe, which is as much as around stars. So they are as much, in terms of mass, they are as much neutrinos as stars, which is the visible matters. Stars are mostly hydrogen. So stars are the hydrogen that combust. So So and then the other hydrogen would around 5%. So out of the normal matter, 10% of those are visible, giving stars, and the neutrinos weighs as much as those 0.5%. So it is a major component of the universe. And of course, beyond this 5%, dark matter, dark energy, and so on are not fully understood. And this would be one of the frontier pursuits in basic science in this century. Okay, now we have the source, and now we want to, having a source, we want to measure it. Now the problem comes, or the fun and the challenge comes. Pauli already mentions that when a beta decay, people do not see the neutrinos. But Pauli would postulate that it exists. What does it mean? It means it just come out and then don't interact with matters. Then you don't see it because you don't interact with its vicinity. So from this, we already know that neutrinos cannot have a very strong or large cross sections. So now we have mentioned that there are strong interactions, electromagnetic interactions, and weak interactions. Pi p is strong, gamma on proton is weak. Neutrinos are only exclusively weak interactions versus energy and versus some funny unit called cross sections in centimeters square or barns. These are not very friendly unit. But to give in the language of everybody can understand. From the cross section, we can turn it into something called mean free path, which is the average distance of a particle of a certain energy have to go through before it interacts, and then that is a measurement of cross sections of how probable that it will interact. And it turns out that for the anti-neutrinos from the reactor on water we know we know water, we know how water behaves well. It turns out that the power reactor neutrinos would have to go through 250 light years of water before it will interact. Okay, so you can see how weak it is. It's not zero; it will interact, but you have to go through a lot of materials to suppress them, to attenuate them. So that's why if we stand next to a power reactor, we don't have to worry about the neutrinos because they just go through our body as if it is invisible. Okay, so now because of this very low cross sections, it poses challenges. How do we study things that do not interact? Yeah, we want to study things. We want to understand a friend. We want to learn more about the friends. But if that friend never talk, never show that what food he eats, and then what doesn't tell people anything, we don't know much about that friend, except that he or she doesn't want to talk. Small cross section. And this is the neutrino challenges of neutrino experiments. How to beat the small cross sections, and the solution is by building massive detectors. But to make it big, that means that keep the cost or the background low. So these are the challenges for researchers. And in order to make the background low, a lot of the experiments are done at underground laboratory. Why underground laboratories? Because this is the cosmic ray. It turns out that there are high energy particles, especially protons, that come from the cosmos, from the outside Earth. When a very high energy protons hit the upper atmosphere, it will interact and give a shower of many different particles. And those showers would just shower down to Earth. Most of them would interact, but neutrinos would go through. So we want to have something to work in a place that are not disturbed, would not be interfered by the cosmic ray charged particles, the cosmic ray that interacts. And how to do it? Then physicists would go to a underground laboratory that has kilometers of rock above. Those kilometers of rock would effectively shield in this 10 to the 6, 10 attenuation like this of cosmic ray. And the deepest one is by now 2,500 meters of rock. 2.5 kilometers of rock is enough to attenuate by a huge factor of the cosmic ray, leaving only the things that do not intact, namely neutrinos, that can go through the laboratory, go through the detector, and then we hope that by building large enough detectors and wait long enough, we will be able to study them, detect them. So this is the rationale of using underground lab to do the experiments. Okay, now, so these are the basics. And fast forward for the last 50 years, neutrino oscillations, neutrino oscillates. There are 3 families of neutrinos, and they can change among themselves. They are neutral as they propagate through space. This is neutrino oscillations from one flavor to the other. We know that there are 3 flavors of leptons: electron, muon, and tau, and they can interchange neutrino of their type. Indeed, the discovery and the studies of neutrino oscillations have brought these 2 gentlemen, Kajita and Madonna, a Nobel Prizes in 2015. But we don't have. And one is on the Nobel Prize for studying atmospheric neutrinos, and also solar neutrinos for the other. And now we will come across this. These are the Nobel Prize worthy data. So we try to understand further what it is. Okay, neutrinos from the sun. The sun. Now, neutrino was first observed from the reactor, but the sun also gives us neutrinos. In fact, the sun gives us electron neutrinos, whereas the reactor gives us electron antineutrinos. Why? Now, if it is a face-to-face meetings, then I will ask the audience. But now it's technically a bit more complicated. So we tell so if you know already, good. But then I will tell the answer. So the power of the sun is from nuclear fusion. Lighter elements becoming heavier and heavier and give out energy. Whereas power of the power reactor is from nuclear fission. Heavy nucleus splitting into 2, lighter nucleus emitting energy. So the direction is different, the process is different. So therefore, one produces electron antineutrinos and the one produces neutrinos. And for the sun, which is from nuclear fusion, essentially it is fusing 4 protons into helium-4. But things are more complicated. It goes through a bunch of nuclear reactions, which we don't have to worry about them. And during those reactions, which are all reproduced in the laboratory to some extent, neutrinos are produced. And we can predict how the neutrinos energy spectrum looks like. And then it looks like this. And this, another Grandmaster Bakao, is a person who championed and pioneered the studies of solar neutrinos energy spectrum. So they calculate all this from the data from the sun and from the data from the nuclear laboratories. Okay, so we know how the sun works, and because we know that, we can predict how many neutrinos are there, energy, and how many. But then, this is not the end of the story. Knowing that this is a prediction doesn't mean that we can clap our hands and go. In the 1960s, Ray Davis in the States set out to really measure those solar neutrinos from the sun. How do they do it? It's from a tank of cleaning fluid having a lot of chlorine. And when neutrinos were intact with chlorine-37, it would produce argon-37. And argon-37 would decay and producing an X-ray of particular energy. And the experimentalists managed to measure how many argon decays, and then from this trace back how many neutrinos are there. But the beauty of this experiment is that, what does it mean by measuring how many argon atoms? Typically, after 1 month of placing this cleaning fluid in the sun, they would be seeing 17 argon atoms in the 600 tons of cleaning fluid. And 600 tons means 2 to the power 30 chlorine atoms. That means that out of 10 to 30 chlorine atoms, experimentalists would manage to measure 17 atoms of argon. And indeed, they can do it. Davis have done it. And the problem comes. They have a standard solar model predictions, but the experiment only observed around 1/3 of the solar model predictions. Picard would predict 17, but you only see 6, 7. Okay, now this has been bothering science since the late 1960s, and it was called the solar neutrino anomaly, puzzle, and problems. When the problem is solved, then there's no more problem, then it becomes a Nobel Prize. But of course, seeing something, measuring things less than predicted, it can be a fundamental, but it can also be a prediction is wrong. After all, we are trying to understand the neutrino coming from the sun. The sun is not in our backyard. Do we really understand the interior of the sun? So there are a lot of problems like this. Or we can question whether the experimentalist has really measured 17. Maybe they are really actually 17, but then the efficiency is not well measured, and then with an underestimation of the overestimation of the efficiencies, then it can easily be observing less. So for 30 years, people has been discussing about other problems other than neutrinos, but they all turns out to be not substantiated. The real problem is the most interesting one, most interesting scenario, which is the neutrinos having mass. Yeah. And pretty soon after having these anomalies, Pontecorvo and Grubov would propose that if the electron neutrinos coming from the sun would oscillate on its way to another type of neutrinos, the muon neutrinos, then there's no problem. Then we should see less. So this is theoretically they are the first to propose this framework. And then by in the 1980s, Herb Chen would propose to use deuterium to do the experiments again, to measure solar neutrinos again, but at a different with a different experiment, different setup. So this is the origin of the SNOW experiment using deuterium. So starting in 1984 as a single author paper by this Professor Chen, but he died very shortly after this paper, so that he was not with the SNOW project for most of the subsequent time, and certainly if he would be living then he would be the one who would be getting the SNOW Nobel Prize. Okay, now fast forward. So the SNOW experiment was proposed 1985, but it would start taking data only at the year 2000. And during the intervening years, other experiments other than chlorine would have seen also solar neutrinos from the water, from the gallium, and also in fact the heavy water, the SNOW experiments in the charge current mode. They are also always seeing on the right, the yellow is the experiment, and on the left is the theory. Always seeing less solar neutrinos than predicted, no matter with which objects we are looking at, or with which technique. Okay, so this is it. So it is a more serious than one experiment, not getting to predictions. Now there are 4 measurements by the year 2000. And okay, now this is the Cherenkov technique with the super chemiocline detector. When a charged particle goes through water, it produces a cone of light, and the cone will tell you the direction where the charged particle is, and how much light depends on the energy of the particle. And this is the technique used by the super chemiocline collaborations in experiments of 50,000-ton big detectors in central Japan, filled with water, and then 10,000 photomultiplied tube, each with this size, half a meter's line, very big. And what is seen here is a bunch of scientists, young scientists, students like you, doing service. Or sitting on the raft in the middle of the mine, cleaning up, fixing cables of the photomultiplied tube in the mine in Japan for the super chemiocline experiments. And these experiments would observe neutrinos from the sun. It sees directions. So the experiments, although it's underground, it knows where the sun is, because the neutrino interacting on electron is preserve the direction of the sun. And this is what the experiments observed. There is enhancement of neutrinos facing the sun, from the sun. So this is a proof that the sun produces neutrinos, of course. Yeah. And you can ask, this amount is from neutrinos, and you can compare with the standard model predictions. And indeed, they are again less, 50% less. And one can also look for this area as a function of time over the year. And there's a variation over the years. So this is what? This is the measurement of eccentricity of the Earth's orbit, because the Earth-Sun distance is not uniform. It's not constant. It's a function of the year. So if one take a deeper look at that, what does it mean? It means that physicists sitting in a mine in Japan, not seeing the sun, not actually seeing the sun visually, knows where the sun is, and in fact can measure the Earth-Sun distance as a function of the year. So this is rather amazing and also amusing. Another amusing fact is that we see the sun real time. These neutrinos are from the sun. It means what? It means that the sun is burning, is in a present continuous tense. When we go outside, today it's very hot, it's summer, and when we see the sun, the heat coming from the sun on Earth is due to nuclear fusion 1 million years ago in the center of the sun. Seeing the sun now only tells us that the sun works 1 million years ago, nuclear fusion. It doesn't tell us whether the sun is working now. Only by seeing neutrinos, which is directly coming from the center of the sun, real time, that we can experimentally measure that the sun is burning. It's really doing its job now, not 1 million years ago. And only the heat that we are receiving from the sun is from a nuclear fusion millions of years ago. Okay, similarly, gallium experiments also would do similar things with like chlorine experiments. It measures neutrinos turning gallium into germanium, and the experiment measures the germanium X-rays, and then again 30 atoms out of 30 tons, a very small amount, but the chemistry and the physics would combine together to make that work. But again, all these experiments measures solar neutrinos, but the solar neutrinos are always less than predicted. So that problem persists, and making it stronger and stronger, more and more believable that there's a fundamental problem here. And then finally, the snow experiment would give us a so-called coffee nail. really solve the problem. How we do it? The snow experiment is a kiloton of heavy water with 1 kiloton of deuterium, and sitting in a mine 2 kilometers depth in Canada, with a in an acrylic vessel surrounded by a lot of the photomultipliers. Yes. So anybody have comments? No. So
Not yet.
okay. So we continue. So are there a stringent time limit? Oh,
Only 1 hour, but you can finish your answer.
okay. So maybe another 30 minutes. Typically, a class would be this long, and then these slides are catered for a class. Okay. So now, so somebody the physicist would build a sub-brief solar neutrino observatory with deuterium, with in fact heavy water in Canada. We don't have to worry about the PMT and so on. It has to be very, very clean, and then of course this is not easy, or else it wouldn't take 15 years to build. Yeah. So why is it so powerful? It's because the other experiments only see neutrinos in one channel. So with one channel, then it is difficult to have an absolute comparison, because it can always exist the possibilities that the efficiency of the experiment was not in well control. But snow is just like our eye. Observe neutrinos in 3 different channels. Now here is the yellow one, the red one, and the green one. Yellow one is the electron scattering, neutrino and electron, which is sensitive to any neutrino flavor. The charge current on deuterium with this is a charge current, only sensitive to electron neutrino. And finally, neutrinos on the deuteron, PN, sensitive only to all neutrino flavor at equal proportion, whereas ES is stronger in electron than in muon and tau. Okay, so with the same detector, same time, it is seeing 3 different channels. It's just like the eye. When we have not just 2 but 3 eyes, then we give a stereo information of the objects, and this is where the power comes from, and this is the beauty of the first paper by Herb Chen that proposed that we can solve the problem by using deuteron. And indeed, 3 independent channels. So we mentioned about the neutral current, electron scattering, and charge current. So the experiment would go out and do the experiments. They are and indeed all 3 independent measurements would be coincident in a single point. But it need not be. There's 3 different measurements. It can be a triangle, but they all overlap in a single point. On this plane, this is the electron neutrino flux. This is the muon and tau neutrino flux, the other neutrinos. So that's why the red one is only a charge current. So the standard model means that I have so much neutrinos at this. If the prediction is here, and we measure much less neutrinos than predicted. But then we now learn from snow that the much less neutrinos doesn't disappear. It turns into other flavors. This flavor that do not behave like an electron neutrinos, but nevertheless like a proper neutrinos, the standard model neutrinos. And so this is the solution of the solar neutrino problem. The electron neutrinos somehow is converted, changed into another active neutrinos, like active standard model neutrinos, which we know that it is and there are 3 families we learn from other data. So they are the muon and the tau neutrinos. the total number of neutrinos remains the same. And this is the power of snow that gives, within one experiment, 3 different measurements and solve the solar neutrino problems, which leads to the Nobel Prize. Okay, now another chapter, atmospheric neutrinos. So we have just mentioned that the high energy cosmic rays would would hit upper atmosphere, producing showers, produce a lot of pions. Pions give muons, muons give electrons, and whenever there's a decay, a neutrino comes. So a neutrino is everywhere. But now, since neutrino is everywhere, so one can see that if it is the distance between the production point to the detector depends on the angle. So the beauty of this measurement is that to relate a measurable quantity angle with the production point, which is the distance that it goes through. So measurement of theta is the measurement of distance. So the experiment tries to measure the ratio of muon and electron type neutrinos as a function of angle, which is as a function of distance, and see what happens. And this is done by the atmospheric, by the super chemiocandidate experiment, which was built initially in the 1970s to study proton decay. So the message is, the experiment was first built to study proton decay, and for proton decay, atmospheric neutrinos was the irreducible background. Both experiments, but nobody ever sees proton decay. So, but they see supernova neutrinos, and the Chemioca project observe anomalies of atmospheric neutrinos. And so atmospheric neutrinos start off as an irreducible background to become the signal. So this is one of the another interesting development in science, that a background, if you study it properly, will turn into a signal. It turns out the background is more important than the things that you initially look for. Okay, now, so how does it work? In the first experiment, the first Chemioca experiment, even in 1988, they observed that as a function of angle of the so-called zenith angle, which is the direction of the muon to electron ratio from the data to predictions. If it is coming from the top, which means the distance is small, there's no problem. It agrees with the standard model. But if it is from the other side of the Earth, it has to go for a long distance. It is D-phase. So there are less muon. The data is less than the predictions. We have less muon neutrinos coming from the other side of the Earth. Okay, so this is starting from 1988. And we mentioned about the super chemiocandidate experiments. So they have done solar neutrinos, but it has also done atmospheric neutrinos. And then we mentioned about the Cherenkov technique. Yeah, right. So what it does is, this cone is from an electron neutrino event, from a muon event, and from a charge current event. So in words, just by hand waving words, is that the experiments would have to measure a lot of those, decide whether it is this one, or this one, and the amount of light, amount of heat is the energy, and how the orientation of this circle tells us the direction. And if you measure a lot of them, do a lot of statistics, count your fingers, and then there is everything about the experiments in a totally condensed way. Now, okay, now so after many PhDs would have done all the finger counting, then in 1998 it finally announced that essentially the same message as before, that when the cosine theta is 1, that means neutrinos coming from the top. There is no problem. always agrees with standard model. If there's no oscillation, it's always the red. But the data is deviates from the red. Always that when the neutrinos have to go through the diameter of the Earth, it changes its flavor. The muon neutrino disappears when it has to go for too long. If it's a short distance, the muon neutrino is okay. But then if the muon neutrinos go for too long, then it is not okay. So that is the issues. Yeah. Okay. So and by measuring this, it is again a very robust measurements, self-contained, self-normalized, that nothing to do with efficiency because it's the same detector measuring up and down, and the down is less than up, as simple as that. And it shows that muon neutrino disappears, electron neutrino is okay, and further studies shows that the muon would return to a tau neutrinos, and it is again neutrino oscillations, which brings along Nobel Prize. Okay, now so these are the very important chapters of science. It goes first, but now after measuring the reactor and the solar neutrinos, we can also study it in further details with accelerator. So in how an accelerator works is when we have a accelerator, neutrinos would have a much higher energy, 1 to 10 GeV, and you can a muon, a proton, a neutron, and a photon would appear differently in an accelerator detector, in a collider experiment. For instance, we have tracking electromagnetic calorimeter, hadron calorimeter, muon chamber, and by in effect, well, just like Eric's experiments, if you measure every track, whether it's like this one, or this one, and then you count the energy, and then you do a lot of statistics, a lot of finger counting, then you characterize the event, and then that is essence of the experiment. And neutrino was seen in the bubble chamber picture. So a neutrino hit a bubble chamber would produce tracks. These are some historical pictures, and it has also seen in an experiment like this. So a neutrino comes, hit a target, and then producing a muon in both cases with an accelerator. Yeah, and in a modern experiment, they use liquid argon time projection chambers, like in the Dune experiments in the States that is being built now, and they can see all the tracks in very exquisite details with this technique. Or you can see in a very precise manners with nuclear emulsions, they can see a tau. Why do we know when the tau neutrino will hit, they produce a tau will decay, and then within a millimeter the tau will decay. So by the nuclear emulsions is enough to see a tau decay into its daughter particles and discover the tau neutrino. So accelerated neutrino have contributed substantially since the first discovery, and historically there are long baseline accelerated neutrino projects from the U.S. Fermi labs to Sudan, Minnesota, or from the KEK and the Tokai laboratory to the Kamioka mine in the same Kamioka detector, or from CERN to the Italian Gran Sasso underground laboratories. So different places have done underground experiments, but with a beam that produced very long distance away, hundreds of kilometers, several hundred kilometers. And no matter, so we would not have to go through too much details on this, but no matter what you look, it's always neutrino oscillations. Neutrino disappears. If there's no in the Japan, so if all the neutrinos, muon neutrino would survive, it would be like this, the dotted line, but the data shows like this, and then it's again in the Fermi lab, not the red, but favors the blue one, which is with a muon neutrino disappearance. So again, we confirm that neutrinos disappears when it goes through distance. Muon neutrinos, therefore neutrinos oscillates. Also the similar case also for reactors. That reactors neutrinos also oxidates, and then this is a Cameron experiment also in a chemical mine, a kiloton liquid scintillator detector sensitive to power reactors hundreds of kilometers away. And indeed, again, we don't have to get into details again by now. So if no oxidation, it is like this. Whereas with oxidations, and then the data shows that it is the reacting neutrinos. Now this is electron anti-neutrino also disappears when it has to go through for too far distance. This experiment also measures the neutrino from the sun. After all, from the Earth. After all, the Earth has a lot of uranium and thorium and also potassium. Uranium and thorium would have these are heavy atoms. They are not unstable. They will undergo a lot of beta decays, and each beta decay gives out electron anti-neutrinos, just like the beta decay in a laboratory. And those neutrinos from the Earth is also measured first by the Cameron experiment, and then subsequently by the newer experiments, Borexino, and so on. So, and from this, by seeing how much of this terrestrial neutrinos, geophysicists can estimate what is how much power is in the radioactivity on the Earth and in the core, from which we share some information on some geophysical models. Another class of experiments is the reactor neutrinos of Taipei, Reno, and then Taipei. So they measure smaller deviations if there's no oscillations. It's like this, and then for small if they are sitting at a distance of around 2 kilometers, a shorter distance, but then they are seeing more neutrinos and trying to see smaller difference from the standard model, and measures another mode of neutrino oscillations, because there are 3 families, and there are 3 families. There are different ways to from A to B, and from 1 to 2, 3, 1, and so on. So there's with 3 angles, and this is the last angle to measure, but turns out to be the most accurate one that is measured. So we measure the angle from the one mode is from the solar neutrinos, one mode is the atmospheric neutrinos, which is also the mode for accelerated neutrinos. And now this shorter baseline neutrino oscillations with theta 1,3 measures the final angle. So all 3 different angles, all 3 different channels of oscillations has been measured now. So this is compelling evidence of that nature really works like this. Now, so how things evolve. Now, so okay, so okay, so I have some glitch in my screen. So you are seeing my screen, right? If you don't see neutrino oscillations, 2 family language, then you should shout.
Yeah, we can see.
You can see it. Okay, now okay, so now these are now we have mentioned a lot of the experiments of the data, but how to interpret it is another story, of course. Remember that in the very beginning we said that we have full understanding when we can turn it into formula, into numbers, and this is one way to attempt to do that. If it is 2 families, it is written like this, and the 3 families, it will be writing like a matrix. We don't have to worry about the difference. So the 3 neutrinos is a mixture of 3 so-called mass eigenstates. Okay, so it's mass eigenstate, and then there's a matrix. So we want to measure this matrix, and there's it. So and the textbook and also elsewhere you can come across a formula like this in neutrino oscillations, and with meta effect the formula is slightly changed into something like this. We don't have to worry about the details of the matrix at this point. Only the message that everything that we said, neutrino oxalates, can be turned into very vigorous mathematics in terms of formulas, which is characterized by numbers. So this PV, PMNS, it's a 3x3 matrix. Each element has its own numbers with error bars. So this is the key message. And there is a twist that when neutrino will oxalate when it goes through space from one flavor to the other. But in matter, there is a mechanism that can enhance it, make the oxidation bigger. Bigger is because electron neutrinos, matter consists of a lot of electrons, but not muons and tau. And because of some structures of the standard model, when one goes through the mass, it turns out that when the neutrinos would go through the sun, there is a matter effect, and some of the oxidation amplitude can be amplified. And these are the three gentlemen MSW that first point out that neutrinos can have such effect. And in fact, by now the studies of oxidation have to incorporate into that effect to do precision measurement. So this effect exists and has been measured. Skipping all the details. So what should be known is that year 2000, there's a lot of experiments, a lot of allowed region here from the super K, and these are the excluded region by various experiments, and then the allowed region. 2002, because of the super K and then the snow experiments, turned it into the very focused. All this allowed region suddenly condensed into a much smaller parameter space. So this is a log plot of mixing angle as well as a delta m squared. So oxidation, the mass, but tells us that it depends on not the mass, but the mass difference of the two mass eigenstates, and also the mixing of the two, of quantum mechanical mixing of the eigenstates. Okay, so global fit. So it turns into a big space into a very small space. And finally, with Kamlan and Minos and so on, it turns it into a smaller and smaller space, more and more restricted. At first, we are swimming at the sea. We don't know where to look for things. But now more and more with every genre of experiments, because of the theory, we can pinpoint into more and more precise numbers. This is how science proceeds. Saying that neutrino oxalates is not enough. We have to turn it into numbers. We have to turn it into precise numbers. Yeah. And then so these are the historical trends from 2002 that eventually it becomes numbers like this and then allow region like this. And also we are seeing that oxidations and then the oxidates means neutrinos would disappear and then reappear. And the experiments like Kamlan and Super Kamiokande successfully see that the neutrinos reappears. So all the fine details would be studied since its first discovery. Okay, so by 2015, this is a historical plot. All the experiments that set limits, saying that it cannot be there, and then at some time there's an allowed region of very big space, and by some but at the end, the allowed region, the answer is either here, here, and here, out of this log plot of huge parameter space. So this is how science make progress from. We don't know nothing about this, but when 50 years ago, but now we can pinpoint a definite parameter space. So which means what? Means a lot of people have contributed. So it's not just experiment that measures. It's also a lot of experiments that exclude different areas. It's also very important. So this is how science make progress. We make a lot of mistakes, but eventually we get the right answers. But making mistakes is, or having the wrong guess is also part of science. So I make a statement here: science make progresses by dispatching 1,001 competent teams to look for things, knowing that the odds for each one of them is only 0.1% in each. Okay, so if I have 0.1%, but I have 1,001 people doing it, one person on average would succeed to get that pot of gold. This is in some spirit is how we make progress, to learn and discover new things. Okay, so the neutrino oscillations. Now these are the various steps I would the various phases. First of all, we have to confirm incomplete understanding. When we are seeing a measurement is less than predictions, it can be anything. At the end, we know that it is due to something important. Now this step is probably the most difficult step. Once we confirm that it is of something important, then we have to define what it is. What are the crucial parameters? In this problem, it turns out that the crucial parameters is delta m squared and mixing angle. So this is not obvious. Okay, oscillations. So once we say that it's something fundamental we don't understand, we have to know that which are the parameters that is important. And we start off drawing things as exclusion plot. Not this, not this, not this, on a log scale. And then eventually it becomes allow region in a log scale. And eventually it becomes allow region, measure region in a linear scale. So we have been working with log plots for a long time. And then eventually, when things are getting more precise, we present our results in the linear scale, like as in Camlin. And from linear scale, we don't draw oxygen curve like this. We just present numbers. The numbers are x plus and minus y. So this is how science will make progress. This is a sign that we understand things better and better, more and more precisely. Okay, but we understand a lot. It's just like the same spirit of the method standard model, but there are still something missing things that we do not understand. What are the remaining things that we do not understand? Is that I mentioned that there's a mixing angle, so which is a 3x3 mixing, and can be breaking up into a 3 of this angle of this this is a mathematics formulation of the 3x3 mixing angle. We don't know about how the second and the third and the first state mass eigenstate the structure is, and we do not know about whether they are CP violations, and we do not know about the mixing, the absolute mass. In pictorially, we now know that it is. We now know that they are. We don't know that there are 3 neutrino mass eigenstate. We do not know whether it is this so-called a normal hierarchy, or it's like this, so-called the inverted hierarchy. And we don't know the absolute scale. So this is delta m squared, but we do not know where is the 0. The 0 can be here or can be here. We don't know. Yeah. So this is our lack of understanding of the complete pictures. Or in another form, the numerical form, the matrix would look like this, or in terms of angle, that would be these are 2 different ways to write this matrix. Remember we have to get into numbers, precise numbers, before we can say that we fully understand the fully in control of the situations. Okay, now so there's a lot of information here, but this is not to explain, but just to give you a feel that the new generations of experiments will have to probe finer and finer problems, structures, which means that it has to put in more and more ingredients to the mess, to the theory. And so the formula, several pages ago, is very simple, and it becomes more and more complicated. Muon neutrinos to electron neutrinos becomes more and more complicated when you have to put into CP violations, put into three flavor, have to put in matter effects, and so on. It becomes more and more complicated from the simple, intuitively, two flavor oxidations. But nevertheless, theoretical physicists have given us all these formulas, and now then experimentalists would have to proceed and work out and then measure them. But we won't have to go. Don't have to get into details of all this, except that there are new projects, ongoing projects, continuing project in Japan, from the Tokai complex to the Kamioka mine, simple Kamioka, as well as from Fermilab to Minnesota, the NOVA experiments, that is trying to study the complicated formulas I showed just now. That has to include three neutrinos, matter effect, evaluation, and different mass ordering, and so on. Yeah. Okay. Now, the data of those, no matter where they look at, data is different from prediction of no oxidation. So oxidation is the neutrino disappears. Muon disappears. It is a very solid flat fact, well measured. And also definitely, muon neutrinos goes to electron neutrinos at the accelerator, and also anti-muon neutrinos go to electron neutrinos. So it's all this data would be showing this with this new generation of experiments. And in the future, we would like to see probed whether there will be CP violations, whether neutrinos oxidations and anti-neutrino oxidation is either identical and the same. This is not proven yet. And if there are some difference, then that gives a very interesting possibilities of explaining, of leading to the asymmetry of the universe, because we know that in our universe, matter and antimatters, we have a lot of matter, but we don't see antimatter, we don't see anti-stars, and so on. So it is one of the big problems in science. So anything that would have CP violations may be related to this, and then people are hopeful that neutrino sector in the lepton would have this possibility, and therefore may have some hints of telling us more about the asymmetry of matter antimatter in the universe. So the future of the neutrino studies is focused. One of the primary goals is to understand more about CP violations in the lepton sector, the neutrino sector. But that is the verdict is still out. We do not know yet. So, and there are experimental science. We are building big detectors, big water Cherenkov detector, big liquid argon detector, and also big liquid scintillator detector, bigger and bigger. For the reacting neutrinos for liquid scintillator, liquid argon and water Cherenkov would be for the accelerator. Now in construction, so at the Fermilab, which the Dune experiments, I believe that there's an India participation in this experiment. So from Fermilab goes through 1,300 kilometers of rock into the Minnesota mine, where there would be a very big liquid argon detector, liquid argon time projection chamber. And then in Japan, there would be a bigger version of the Kamioka experiment called hyper Kamiokande, where again water Cherenkov detectors with a lot of PMT covering it. Okay, so now this is neutrino oxidations, but in the remaining minutes I just mentioned, but we're not going into details about what are the things of studying neutrinos that we are doing. We're studying neutrinos from cosmology. Cosmology will tell us about neutrino mass. We study neutrino double beta decay that tells us about whether neutrinos is its own antiparticles. We try to look for neutrinos from the supernova. We also do neutrino mass measurements with beta decay. Beta decay gives neutrinos, and for instance, in this picture, the capturing experiments that shows that. Remember that I mentioned that the absolute neutrino mass is still an unresolved issue. What is absolute scale of neutrino mass? We don't know. We don't know the difference, and therefore, this capturing experiment is a very big. Now this is real. There is a very big chamber. They tries to measure the beta decay of beta decay energy of a tritium of a tritium electron from tritiums, and tries to and through the electric field screening and so on. We don't have to worry about the details, to measure very precisely how its endpoint. If neutrino mass is 0, it will be the red, and neutrino mass is 1 eV, it will be like this. So it will be shifted by 1 electron volt out of 17, 18 keV. So it's a very small difference with very small statistics. And so this is what the experiment is trying to do. Neutrinos, whether neutrino and its antineutrino is the same particle but with different spin, is a question of whether it is a direct neutrinos or Majorana neutrinos. And to do this, one would have to study neutrinoless double beta decay in an atoms. If, for instance, in this example, a molybdenum can decay into rubidium 100, and there would be an endpoint where the 2 electrons would combine to the same energy, and it would see this. The neutrino would be a Majorana particle, and this is one of the interesting and important subject of neutrino physics. We also study neutrino from the astrophysical sources. In astrophysics, people have measured all the charged cosmic ray spectrum, has measured gamma rays, but since the source would produce gamma ray or produce high energy proton, then one should expect that they should also produce neutrinos. The good things about neutrinos is that also produce gamma rays is that they will preserve the directions of all of the source, unlike charged cosmic ray where the direction is totally lost. And indeed, experiments, there's several experiments, and then the biggest one is the ice cube experiment at the South Pole, where the experiment would insert a lot of photomultipliers tubes into kilometers of rock, of ice. So ice is also just like rock. It's a shielding. It shields the cosmic ray, and it put in a cosmic photomultipliers tube, pretty much like the super Kamilkani experiment, and see the shrink of light from ice, and they successfully observe high energy cosmic ray like this. So now we're talking about totally different 10 to the 4 TeV. TeV is 10 to the 12 eV, so this is around 10 to the 15 eV, very high energy cosmic ray, very high energy neutrinos from the astrophysical objects, and successfully measured by the ice cube experiments in the South Pole. And they can, and then from events like this, they can also measure the directions, and then eventually we would like to see, not just we see the neutrinos, we want to see the neutrinos from a particular source. And eventually, this measuring neutrinos would have to integrate it with measuring cosmic ray, gamma ray, X-ray, and gravitational waves to become multi-messenger astronomy. So the new era of doing astronomy is to study an objects in the sky, but then not just look at electromagnetic spectrum, but also look for neutrinos and hopefully also gravitational waves to learn more about those objects. And indeed, we have already seen supernova neutrinos from 1987A on the supernova, and from the Kamioka, as well as the Aksan and the IMB experiments. The next supernova will tell us more about what we will be able to measure the oxidation parameters, as well as learn more about by seeing how the neutrinos would evolve with time, and also how the ratio of all this will tell us more about oscillations, as well as with how the supernova works. And neutrino mass, and I mentioned it several times ago, also related to cosmology. By studying cosmology, also tells us about neutrino mass. For instance, Big Bang nucleosynthesis, by studying how many helium and deuterium and helium-3 and lithium in the cosmos, and then all these are primordial, so-called, starting from the Big Bang. How is the ratio compared to photons? These are the matter compared to photons. Will tell us about how many neutrinos are there, and then in fact, this is the measurements that tell us about that there would be around 3 neutrinos, because there are more neutrinos, there are more energy density, and they will change the expansion rate of the universe. But the expansion rate is by now very much constrained by data. So we learn more. We learn about neutrinos, how many neutrinos, and some of their properties by studying the primordial element distribution. By studying the cosmic ray background, so also tells us about how many neutrinos are there. So this cosmic microwave background, if the neutrinos would change the energy density slightly, and then it will shift all the multiples of the multiple of the position of the CMB spectrums, and then we measure one, and from this we conclude that it's again consistent with 3 neutrinos. Yeah. So Big Bang nucleosynthesis is 20 minutes since the Big Bang. CMB is 400 kilo years from the Big Bang. They give consistent results, which is 3 neutrinos. So cosmology tells us this. And the cosmology tells us about the structure formation from neutrinos. So this picture is, one is simulation of cold dark matter, and one is real measurements. You cannot tell which is which. So which means that a cold dark matter scenario, not neutrinos, will explain well the structures of the universe. If the neutrinos is dominated the mass of the universe, if the dark matter is due to neutrinos of very light nature, the universe will look like this, totally different from what is observed. And from this, we learn that we would learn that the dark matter neutrinos would not constitute the big portions of the dark matter. Dark matter needs to be different objects than the standard model neutrinos. Yeah. And by measuring and twisting it the other way around, that from the distribution of matter, we can constrain how many neutrino mass are there. So dark matter already constitute that much, so there are less and less space for neutrino mass, and then they are placing more and more stringent limit, and eventually cosmology may be able to measure the direct measurement of the neutrino mass when they get to the 0.06 eV. Remember that the Catherine experiments sensitivity is around 1 or 0.1, 1 to 0.1 eV. So cosmology is although it's more model dependent, is providing a more stringent constraints to the neutrino mass scale. Okay, so the future landscapes. So now we start off having a broad view of the standard model of the universe as well as the particle physics, and then we spend most of the time focusing on one particular element, one particular alphabet, the neutrinos, the histories, and then what the big achievements in the neutrino stations, and there's the various things, the various ways that we can study the neutrinos and the current efforts. Now we try to conclude by again showing the very grand landscape. What is science doing? Not just about neutrinos. Yeah. So the bottom line is that the fundamental there is fundamental conflict between the universe as we try to observe or understand it through gravitation or from particle physics. So there are 4 different interactions. There's including gravitation, gravity. I never mentioned gravity until now, but when we couple gravity, then there is problems. Because gravitation is described by general relativity, which is kind of microscopic physics, whereas particle physics is a standard model, macroscopic physics. Both the data and the theoretical formulations, they are inconsistent. Theoretical data is that leads to the dark matter problem. Dark matter is shown that when we understand the universe by gravitation, there are more mass density than with particle physics. And the theoretical formulations is particle physics is with the quantum mechanics, quantum field theory, whereas gravitation is still with classical physics, and there's still no quantum theory of gravity. So even at a theoretical level, they are speaking different languages. So this is the most fundamental problem in the fundamental physics. We should understand it now. 95% of anything in the universe is understood, and this is the mainstream interpretation. It may or may not be like that, and then we believe that because of this, it should be physics beyond what we understand now. We don't understand why the understood 5% is only matter without antimatter. And then we do not know how the physics of the inflation, how to describe the early universe. And we do not know what happens before the Big Bang, or whether it is part of science, whether we can understand it with scientific methods. Okay, but nevertheless, well, I mentioned that these are very big problems, not something that we can solve in 1 month. But just to have a positive note is that science has gone through a very long journey, starting from the ancient Greek, and then I stress that all this long journey starts with very long time ago, 2,000 plus years ago, with the ancient Greeks, when they tried to have a standard model of air, fire, earth, and water. This is the standard model of the world. And they do experiments. For instance, they discover that air is something rather than nothing. And in fact, it takes 2,000 years that we come across we get to the understanding of everything in terms of the periodic table. And 100 plus years ago, Becquerel and the European physicists discovered the radioactivity, discovered the subatomic physics, quantum mechanics. Eventually, it's the completion of the standard model in 2012 with the discovery of the Higgs boson, so that 4% is fully, completely understood. But it all started off with the very humble origin 100 plus years ago with the discovery of radioactivity. And today we learned that that the beta decay, instead of being a monoenergetic, is a continuous spectrum, leading to Pauli to postulate that this is neutrinos. And to now we have understanding, we've discovered neutrino stations. We have good understanding on how the neutrino behaves. But still, although there's some remaining problems to really pinpoint the nature of the neutrino mass, and also the structure of the Lagrangian, how to write the formula, how to write the equations exactly. But while the powerful play goes on, because we now have the dark matter problem. So maybe in some future occasions I can give another talk on history of dark matter. But there's a problem. We don't know. So this is one of the first data that shows the dark matter. We don't know what it is, but only that we should have confidence in the power of scientific investigations and the powers of scientific investigators. So we have gone through a long journey. We have a very good record of solving problems. We should be able to solve this one. Okay, so summary: neutrinos are important for strange objects. History of neutrino physics is full of surprise. Today we stress more on the saga, the epic of finding, studying massive neutrinos and the finite mixing. But neutrinos is more than this. It relates to astrophysics and other areas. And neutrinos is the first avenue of physics beyond the standard model. There are more experiments and projects coming up. And neutrinos, both as a theory as well as experimental techniques, for instance, underground experiments, may also be an avenue to the study of dark matters, both in terms of physics as well as an experimental techniques. So with this positive note that I conclude, I hope that you have learned something and then pick out something from the talk. It may take longer than it seems, but I hope that everybody will find it worthwhile. Thank you. Thank you.
Thank you, sir. Thank you, sir. Thank you.
Chair. Okay.
I would like to request secretary of this science lecture series, Dr. Puneet Ji. You must have a question from the audience side. Please ask on their behalf.
Yes, sir. So, thank you very much, sir, for this wonderful presentation. And you told us the whole story from the proposal for neutrinos to their detection and then current developments in the field. So it was a very comprehensive talk, and in fact, in course of the talk, you actually answered most of the questions that came to the mind. But still, I have some questions from the participants, so I will ask these questions on their behalf. So Mr. Hariom Agrawal asks that what is cosmic microwave background and how it was formed before stars?
What is cosmic microwave background? Okay, so first of all, this is not neutrino, but then this is of course a very important subject. So in simple terms, the universe start off as a big bang. There's a lot of energy, right? So those energy eventually, in a very simple-minded discussions, those energy have to evolve. So some of those would becomes matter. Some of those would becomes photon. Matter would becomes hydrogen, heavy elements that becomes us. This is part what we are seeing now. It's the matter part of the energy from the remnant of the early universe. But the photon part at first is high energy, but as the universe expands, the energy becomes lower and lower. It doesn't form as much structures, unlike matter. Photon is photon. Photon would not form a bound state. So as the photons start out with very high energy, but as time goes on, 10 to 10 years, the universe expands. It becomes lower and lower energy, and eventually, by now, the energy is 2.7 Kelvin, and which is what we call microwave. But this is from a cosmology, so it is cosmic microwave background. So this is the cosmic microwave background is the evolutions of the universe from the early stage.
Thank you, sir.
It is cosmic. It is microwave because it is cooled down. And similarly, related to neutrinos, there's also cosmic neutrino background, except that we haven't seen it yet. It is very difficult to be measured, but measuring it is a huge feat. is a cosmic neutrino background. And then similarly, if neutrinos start with high energy, but as it expands, then the energy gets lower and lower. And by now, the neutrino energy is 1.9 Kelvin, very low energy, or in energy unit is around micro electron volt. Yes, so this is cosmic microwave background. And by studying the cosmic microwave background, both, for instance, measuring the 2.9, 2.7 Kelvin is already tell us something about the Big Bang model. And by looking at the fine structures, whether everywhere in the universe is 2.7 or there's some minor difference. In fact, they are minor to 10 to 10 minus 5, which tells us about how the universe evolved. What sort of matter are there in the universe? So by studying the fine details of the cosmic microwave backgrounds tell us a lot about how the universe evolved. Yeah.
Thank you.
In simple minor terms. Yeah. Again, everything that I say, I try to give a broad view, but every sentence is a PhD thesis, and sometimes it's a whole generation of scientists working in a project to produce. So while we want to learn more, but let's not let's be reminded that this is not by no ways trivialize or make it small the achievement. Yes. Okay.
So Simran Verma wants to ask that what must be the energy of neutrino for reactions to occur, interactions to occur, perhaps?
On paper, any neutrinos, the grammar tells us that any energy neutrinos would interact with matter according to some standard model formula. But it happens that, as you can easily imagine, is that heavier or higher energy neutrinos have larger cross sections. So there's no strict answers that below a several energy neutrinos do not interact. No, it just interact less and less, more and more difficult. Whereas higher energy, but so there's a dynamic. Most neutrinos are lower energy, but the lower energy have less probability to interact. And also when it interacts, because it has low energy, it is less easy to be detected and more vulnerable to background. So it's more difficult. Whereas high energy neutrinos, like 10 to the 18 EV neutrinos, when it has higher cross sections, but they have much less in terms of amount. You have to wait for 100 years for in a kilometers to see one event. So there is a trade-off. Yeah. So there's no strict energy threshold for neutrino detection, but at very low energy, it is experimentally very difficult for small cross section in the big background. Whereas for very high energy, because the flux is much less. So no wonder that the measured neutrinos by now are the intermediate range, starting from 100 keV to by now with the ice cube experiments, it can measure up to 10 to 15 eV.
Thank you, sir. Sir, is there any suggestion about measuring the absolute masses of the neutrinos instead of the mass differences?
So I mentioned that the beta decay spectrum measurement, you measure, but the beta decay spectrum is continuous. Okay, it's continuous. We know that 100 years ago. But if we want to measure the end point, it is a measurement of neutrino mass. You can imagine that the end point of the beta decay would have to be electron energy plus the neutrino mass becomes the so-called Q value, which is the mass difference between the parent and the daughter nucleus. So if one measures that very precisely, we would be able to measure the absolute range, absolute value of the neutrino mass. And indeed, we saw that Catherine experiment.
Yes.
a very big, that very big barrel that is winding through a village in Germany, a very impressive scene. That is an experiment that tries to do that. Another line of attack is with the cosmology, because the neutrino mass, if its neutrino is too heavy, it would affect the energy. But there's a lot of neutrinos out there. Even heavy neutrinos would have effect on the energy budget of the universe, and therefore would affect some of the measurements of the CMB background and so on, and also the structure of the galaxy matter. So by studying all this, we also tell us about the absolute neutrino mass scale. We have no firm numbers yet, but these two subjects are also very, very prominent, very frontier research subjects.
Thank you, sir. Another question? Yes, sir.
If we have more questions, then we can send their question to the speaker, and later on we can get a comment, and then we can send them again. So
Okay, sir.
We are just stopping here the question and answer session. And dear participants, we really heard a very interesting journey from basic to advancement of neutrino physics with full of information, a lecture on neutrino physics overview in a very popular way, delivered by Dr. Henry Wang sir of Institute of Physics, Academia Sinica, and we really see a very interactive question and answer session too. I request our coordinator, Dr. Vijay Raj Singh ji, please give a vote of thanks.
Thank you, sir. Good afternoon to everyone. And I am honored and lucky to have opportunity to give a vote of thanks on this special day. I particularly liked Professor Henry Wang's talk, where he explained the basic concept of neutrinos, its sources, some technical issues, story of solar neutrinos, atmospheric neutrinos. The way he explained was really very extraordinary. And I would like to thank all my friends, teachers from CUSB, particularly Dr. Sahi Sahab, Dr. Chandra ji, Dr. Lakhvinder ji, as well as faculties from outside of the CUSB, who always helped us, suggest us to organize such wonderful webinar. I must not forget to thank the students who always gathered in such a great number and show their interest in such webinar series. Finally, I again want to thank the head of department and the chairman of this science lecture series session 2, Professor Venkatesh Singh, respected my fellow coordinator Professor Budhendra Singh, and secretary Professor Puneet Misra ji for participating in this seminar. I would like to thank you once again for making this event a great success. Thank you. Now I request Professor Venkatesh Singh to allow to close this session and announce about next talk. Professor Venkatesh
So
Singh.
thank you, sir. Thank you, Wang sir. Dear participants and colleagues, that's all for now. We will see you on August 29 at 11:30 a.m. with another wonderful speaker, Professor Preeti Hove of Indian Institute of Technology, IIT Indore. She will speak on study of magnetic and Martin-statistics transition in NIMNGA type Hausler alloy. Until then, stay safe, stay healthy, and keep thinking. Goodbye. Namaste, sir.
Okay, so thank you, everyone.
Thank you, sir.
Thank you, sir. Thank you so much.
I enjoy the occasions, and maybe in the future, I'm happy to talk again if you.
Sure, sir. Sure.
Okay.
Sure, sir. Sure.
So bye bye.
Thank you, sir. Bye, sir.